Hey, Los Altos students, welcome back from spring break. I hope you enjoyed your break and feel rested and ready to go. We are almost done with logs. We have about 3 more lessons to go. This is your last lesson before the quiz, and then a few more lessons before the test. This one, we're solving exponential equations. So it's a little bit of application of the change of base and using it in word problems. So let's review change of base. It has been a week. So let's say I have a log that does not have base 10. So common log would be base 10, natural log would be base E. So let's say I have a log with something other than 10. We'll call it B. And the change of base, we're going to change it to common log, which means base 10. So we'll have log A over log B. Both of these now have base 10, and you can put them in your calculator. You don't have to write the 10 in there, but I will just as a reminder. So we do have base 10. You'll be using that in these problems. Our goal is to apply those skills that you've learned so far to these word problems. Introduction. A population of bacteria doubles every day by the function P of t equals 2 to the t power, where t is the time in days. What is the value of t when there are 10 bacteria? All right, so we're given some information. We're given that 10 is the number of bacteria. That would be our P of t, the total amount at the end. What we're searching for is t. So I could go ahead and plug in the 10 for P of t and then find t. Now, remember, whenever your variable is the exponent, you're going to need to use log. So you're going to change from exponential form to log form. So let's do that. This will be log base 2 of 10 equals t. And now we'll use that change of base because this is not base 10. Log 10 over log 2. Log 10, remember the base is 10, so you're asking 10 to what power is 10, so that'd be 1. You don't have to do that or know that right off the top of your head, but that is something to kind of look for and recognize. So in my calculator, I'm going to put the 1 divided by log 2, and I'm going to get about, let me put that up here, 3.219. And this was days, right, for a unit. We are doing word problems, so add your unit to your answer. Now you might recognize this. This was what we started with the very first lesson. Mr. Tran said, how do we find t in this exact problem? 2 to the x equals 10. And you used your calculator and kind of narrowed between the fact that it needs to be between 3 and 4. And then you went to the 10th decimal place, and then hundredths and so on, and kind of, got it to, I think, about 3 decimal places. And then we learned about logs. So this is kind of a familiar problem. In order for us to understand how exponential equations work, I want to take the same problem and kind of make a table here so that we can kind of figure out what a general exponential equation should look like and what the pieces are and what they mean. So let's start with number of days being 0. What if we had 0? Now we could plug that into the equation, right? 2 to the t power, 2 to the 0 is 1. And then we'll move on from there. And then after 1 day, we know that we would have 2. And then after 2 days, we would have 4. After 3 days, 8. And after 4 days, 16. Now what we're doing here is if the initial amount is 1 and we didn't double it because no days have gone by, that's actually what it looks like. And in the second row, this would be, we started out with 1 and we doubled it, so it would be times 2. And then after 2 days, we start out with 1, we doubled it on the first day, and then we multiplied it by 2 again to double it on the second day. And let's go one more. So again, let's say our population started out, it was 1, and then we doubled it after the first day, and then we multiplied by 2 again on the second, and then we had to multiply 2 again on the third day. So we can see a pattern here where I'm multiplying 2 times 2 times 2, which in the equation here, right, the shorthand way of writing multiplication is to raise it to a power. Now the number 1 there, where did that come from? It wasn't explicit in the problem, but basically we were starting with a population of 1, and then it was doubling every day. So we have an initial amount, and then we have some rate of growth. And that is what we need to know for our general exponential equations. So for example, again, very general here, might look something like this: y equals a times b to the x. It can be a little bit more complicated, and we will investigate this further later on in this unit and in the next unit. But for now, this is very general, where A is your initial amount. And in this case, it was just 1. And then B is some sort of rate, and it could be a rate for growth, or it could be even a rate of decay. But it'll be given in the problem, some sort of rate. X is usually time of some sort. That's your independent variable, and it's usually time. And then Y could be whatever it is. In this case, it was number of bacteria, population of people. It could be even amount of money after a certain amount of time. Y can be that dependent variable. It could be a lot of things. Okay, so that's our very general equation. And then I'm going to do some examples with you here. Having a calculator helps for these because you are, again, doing logs. So number 1, the population of a town in thousands is modeled by the exponential equation. So here you can see that setup. We have an initial amount and a rate where T represents time in years. After how many years will the population P of the town reach 1,000? So the fact over here that this is in thousands. So whenever you get your answer, just remember that there's like 3 zeros after it because this is in thousands. So when we're given the initial, or when we're trying to find the how long until we get 100,000, I only need to be concerned about the 100 there. I'm not going to add 3 zeros to that when I put it into the problem. It's already assumed that there are 3 zeros after that 100. So I'm going to plug that into the problem for my population, and we're going to search for, or find, not search for, we're going to find T. When does that happen? So when solving again for the variable and it's an exponent, I know that I'm going to need logs, but you want to isolate it as much as you can first. So we still need to divide by 52 before we switch to logs. So get rid of the 52 first. This is about 1.92307. I've got it at 5 decimal places because a lot of times we round to 4 decimal places. So you would keep it, you know, at 5 decimal places until you round at the end. You could also keep it as a log or keep it as a fraction. You could do that too. So you could keep it as 100 over 52. Oops. Like this. And that's fine. And then you don't have to use your calculator yet. Either way is fine. And now we're going to change to logs. So this will be log base 3 of 100 divided by 52. And then you'll use change of base. And in my calculator, I get approximately 0.592 years. Actually 5.2. And again, that's in years. So a little less than a year. It's about 7 months. If you wanted to find out how many months that was, you would just take that number and multiply it by 12. Okay. Number 2. Now these are all examples. You can, these last 2, you can just try these, see if you can set it up, and then pause the video and come back to this and just check your work if you'd like. All right. So number 2, I'll go ahead and go through this again. If you want, pause and come back. Harry invests $5,000 in a certain stock, which is expected to increase his investment by a factor of 1.25. The exponential equation is here, models his investment. If his investment grows as expected, after how many years will his money double? So that's kind of a tricky question. So we need to know what that amount is. So the fact that we're told, explicitly here, yes, it's in the equation, but we're also reminded that the initial amount was 5,000. So double means 10,000, right? So we're looking for when will it reach 10,000? So that's the part we're plugging in for A in this equation. Again, isolate the variable as much as you can. So divide by 5,000 on both sides. And you'll get 2. And then change to logs. So this will be log base 2. No, excuse me. 1.25 of 2. The base was 1.25. Use change of base. And you will get approximately 3.106 years. And it did say to give months, but again, you could take that decimal part, the 0.106, multiply that by 12 and find out that that's about 3 years and 1 month. Last one, scientists recently discovered a new type of metal compound, which has a half-life of 16 hours. This means that it has a decay rate of approximately negative 0.043. At this point, we don't really understand where that comes from. We're just going to take what they say and just trust it. If we currently have 20 grams, we can model the decay of the compound with the exponential equation, such as that, where T is time in hours. Okay. Approximately how much of the compound will remain after 5 hours. So we can see here that we have E, and you're going to use your calculator to raise E to this power. Now we have to be really careful that you multiply that negative 0.043 by the 5 and then take E to that power, all right? Then multiply that by the 20 and you get approximately 16.13. And remember, this is in grams, right? So here we go. After how many hours will we have only about 8 grams? So this will be the total amount of the compound, and we're looking for T. So for this one, just a reminder that if you have E as a base, we're going to be using natural logs, right? But let's first divide by 20. And that's 0.4. And we're going to convert to natural log. You don't have to write E because that's the base, but you're taking the natural log of 0.4. Let's see, negative 0.043 T. All right, so I'm going to go ahead and divide this by the negative 0.043. And in my calculator, do this all in one step. So I'm going to hit natural log of 0.4 in my calculator and then divide by negative 0.043. And T will be approximately 21.309 hours. And the question was asking how many hours, and we've answered it. So there you go. All right, your homework, I just wanted to show this to you that the first 7 problems, A through G here, are not the word problems, but it's just review and practice of getting these into log form from exponential form. There's a couple that I think maybe you could use the same base method, but most of these you're just going to go ahead and use your skills that you've learned to solve those. And then you have a couple problems using the exponential equations. All right, good luck.